We start our discussion on a different kind of amplifier. So far we have talked about only single transistor amplifiers. We did work out one or two problems on multiple stages, but this is the first serious discussion on multiple transistor circuits, and the circuit is that of a differential amplifier. Before we take up this topic, I wish to recall what we did last time. Last time I said that in a multiple transistor circuit, or even in a single transistor circuit where there are many capacitances, exact nodal analysis may be difficult. Application of Miller effect may also be difficult, and therefore the methods that are available are the methods of short circuit time constants and open circuit time constants. Open circuit time constants apply to high frequency gain, and short circuit time constants apply to low frequency gain. And if you have several critical frequencies, omega h1, omega h2 and so on, then the overall high frequency critical frequency, or the 3 dB cutoff frequency, is given by 1 by omega h is equal to summation 1 by omega hi. In other words, the time constants, and I have also told you how to calculate the time constants. It is the capacitance multiplied by the resistance seen by the capacitance in the Thevenin sense. This is for high frequency, and for the low frequency, the method of short circuit time constants, it is simply the summation of the individual omega li, individual cutoff frequencies. In general, therefore, the transfer function AVS j omega would be of the form AVS 0, the mid-band gain, divided by 1 minus j omega L1 by omega, this is the low frequency critical frequency, multiplied by 1 minus j omega L2 by omega, and so on, multiplied by the high frequency terms, which will be of the form 1 plus j omega by omega h1 multiplied by 1 plus j omega by omega h2 and so on. Okay. This is the general expression for the gain of an amplifier containing many transistors, many capacitances and so on and so forth. And this calculation is, as I said, approximate calculation based on the method of time constants. And these relationships, that is 1 by omega h is the summation of omega 1 by omega hi, and the other relationship is omega L is summation of omega li. These are also approximate calculations. We would like to illustrate how approximate these are by taking two very simple examples. We consider two amplifiers. This is the symbol for an amplifier, you must have noted by now. Two amplifiers which are identical, let's say A1 and A2. A1 is identical to A2, two identical amplifiers cascaded together in such a manner that the output impedance of the first stage R01 is much lower compared to the input impedance of the second stage. Okay, so that whatever voltage appears across the output of A1 does appear across the input of A2 also. Okay, this is the condition for non-interacting stages, that is A1 does not affect, A2 does not affect the gain of A1. Ri2, we assume that it is much greater than R01. This is the condition to be satisfied. If it is not satisfied, then what do? We put a buffer in between, an emitter follower, which transforms a high impedance into a low impedance. Okay. If that is so, and A1 of j omega is of the form A1O divided by, let's say, 1 plus j omega by omega H1, if each amplifier at high frequencies can be described by such a relationship, then obviously the overall gain will be the square of this A10 squared divided by 1 plus j omega by omega H1 squared, and by our approximate calculation 1 by omega H should be equal to 1 by omega H1 plus 1 by omega H1, which is 2 by omega H1, that is omega H should be equal to 0.5 of omega H1. Alright. In other words, if my gain of individual stage is like this, okay, this is A1 magnitude, this is A1O, and the high frequency cutoff point is omega H1, then by cascading two stages, what I get is, what we will get is something like this. The gain would be, no, I have not been able to draw it correctly. Let's see. Let's use a different color. It will come like this. Omega H for the overall amplifier will be lower. That is, this amplifier, this cascaded amplifier, can go up to not as high a frequency as the individual stage. The point to be remembered is, if we increase the gain, the bandwidth comes down. Omega H1, the bandwidth is omega H minus omega L, the high frequency cutoff minus the low frequency cutoff. So if omega H goes down, naturally the bandwidth goes down. At the cost of bandwidth, we increase the gain. Okay. Now, this is a very simple case where we can calculate the high frequency 3 dB point exactly. Okay. It is not very difficult, because the relationship to be satisfied is A10 squared divided by magnitude 1 plus j omega by omega H1 squared. If the overall high frequency 3 dB point is omega H, then I put a omega H. This should be equal to how much? A10 squared divided by what? For the 3 dB frequency, this should be divided by root 2, not 2, root 2, that is the 3 dB point. And therefore, I can solve this very simply. 1 plus omega H squared divided by omega H1 squared equals to root 2. If I take the magnitude, take this square, or take this square and then take the magnitude, it will be the same thing. This is what you will get, and therefore from this you get omega H squared as equal to root 2 minus 1 times omega H1 squared, or if I take the square root of both sides, I shall get this. And you can easily verify that root 2 minus 1, 1.412 minus 1, that is square root of 0.412, this is approximately 0.64 omega H1, which means that our estimate by method of open circuit time constants, what was the estimate? Estimate was 0.5 omega H1. So our estimate was pessimistic. Isn't that right? It was pessimistic. We anticipated more danger than what it is actually. It is not half, it is 0.64 times omega H1, and there is a deviation, but when there is a large number of capacitors and a large number of such time constants, this is the only method that is available to an engineer. Of course, you can make your life miserable by writing the exact node equations, trying to solve the equation, but you will spend a lot more time than is really called for. Okay, this is an engineering approximation. The point at discussion is that our estimate by the method of open circuit time constants is pessimistic. That is, what we get will be, the actual situation will be brighter than what we get by this estimate. Similarly, suppose we consider the low frequency gain. Under the low frequency condition, A j omega would be of the form A 1 0 divided by 1 minus j omega by, I beg your pardon, omega L1 by omega whole squared. Agree? When two stages are cascaded. This is at the low frequency end. And you can see that the equation describing the 3 dB frequency, low frequency 3 dB cutoff, would be 1 plus omega L1 squared divided by omega L squared, and this should be equal to root 2, and therefore omega L, is this point clear? Magnitude is put equal to A10, I have made a mistake, this is A10 squared. It would be A10 squared divided by root 2. By simplifying this, this is what you get, and omega L therefore shall be equal to omega L1 divided by square root of root 2 minus 1, and this is approximately 1.56 omega L1. What is our estimate by the method of short circuit time constants? Our estimate is twice omega L1, and therefore what we get is instead of twice omega L1, I get a smaller value. I get a smaller value. That means our estimate is again pessimistic. All right. So these estimates are very much favored by engineers, because what you are going to get in practice is a better situation, is a brighter situation. All right. Okay. With this, we close the discussion on amplifier frequency response. We shall come back to this topic after we discuss differential amplifiers and power amplifiers. That is, when we consider wide banding techniques. Given an amplifier, a common emitter amplifier, it has a certain bandwidth. Now we want to increase the gain, and we also want to increase the bandwidth. So what do we do? How do we wide band an amplifier? And we shall see that we will encounter more than 2 transistors, and we will see that the method of open circuit and short circuit time constants are very, very handy methods for calculation of the performance of such amplifiers. Now, on the topic of differential amplifiers, what is a differential amplifier? The symbol for any amplifier is this triangle. For a differential amplifier, we write DA, differential amplifier, and for an operational amplifier we write OA. Okay. For any other kind of amplifier we don't write anything, we simply draw this box. Now a differential amplifier has 2 inputs. One is a non-inverting input and the other is an inverting input. Now this voltage we shall call V1 and this voltage we shall call V2. Okay. V2 is the inverting input. It is not an op-amp though, it is not an op-amp, it's a differential amplifier. And the definition of a differential amplifier is that the output voltage, single-ended output voltage ideally is some gain A multiplied by V1 minus V2. Okay? Ideally, this is the ideal situation. Now it turns out that ideally if V1 and V2 are equal, if these 2 terminals are clipped together and the same voltage is applied, the output should be 0. It turns out that in practice the output is not equal to 0, and therefore the gain that we get here, we call this a differential mode gain. Okay, A sub D is called differential mode gain and no longer ideal. It turns out that if V1 and V2 are identical, the output is not 0, and therefore to this we must add another term, which is the common mode gain A sub C, C for common mode, that is when the two voltages are identical, and we put V1 plus V2 divided by 2. Okay. You can see that if V1 and V2 are identical, then this term would be 0 and the output would be AC multiplied by V1. Is that clear? That's why the division by 2. Okay. A sub C is called the common mode gain. Common mode gain. And accordingly, these two voltages, that is V1 minus V2, is called the differential mode signal, and we use the term V sub D for this, V sub small d, and V1 plus V2 divided by 2 is called the common mode signal. And the term for this is V sub small c, okay, common mode signal. Ideally what we want is that when V1 and V2 are equal, the output should be equal to 0. The output should only be proportional to the difference between the two signals. The practical situation is that there is a common mode signal, there is a common mode component in the output, and therefore for a non-ideal differential amplifier, the output voltage is given by A sub C, V sub C, the common mode signal, plus A sub D, the differential mode gain, multiplied by the differential mode signal. The definitions are that V sub D V sub D is equal to V1 minus V2, and V sub C is V1 plus V2 by 2. Obviously we should be able to write V0 in terms of V1 and V2 also. Instead of Vc and Vd, you can expand this, and therefore you can get V0 equal to A1 V1 plus A2 V2, and the definitions are clear. This is another way of writing the same equation. The definitions are clear. Measurements can also be made. For example, if you want to find out A sub C, the common mode gain, obviously this is V0 divided by, you want to make this term equal to 0, so V0 by V1 with V1 equal to V2. Agreed? So you clip the two together, apply a voltage, measure the output, then V0 by V1 is equal to this. Similarly, A sub D would be V0 by 2V1 with, you want to kill the common mode signal, so you make V1 equal to minus V2. If you make V1 equal to minus V2, then V sub C will be 0, and this will be twice V1, and therefore V0 by 2V1 under the condition V1 equal to minus V2. So given a differential amplifier, you can measure A sub C and A sub D very easily in the laboratory. These are all small signals. These are signal quantities, not DC quantities. Okay. Similarly, if you want to measure A1 and A2, it's obvious, V0 by V1 with V2 equal to 0. That is the inverting terminal you connect to ground, apply a V1 and measure the output. Similarly, A2 is equal to V0 by V2 under the condition V1 equal to 0. So all of them can be measured in practice. You also notice that A sub C and A sub D can be expressed in terms of A1 and A2, right, by simple algebra, and I shall not repeat this. I will simply write down the expression. AD, well, AD is equal to A1 minus A2 by 2 and AC is equal to A1 plus A2. They are very simply related. So, measuring any two of these parameters, of the four, any two of these parameters suffices to characterize the differential amplifier. Question: why should we bother about a differential amplifier? Why should we bother about amplifying the difference between two signals? Take a very simple measurement situation, the Wheatstone bridge, which you use to measure impedances. There are four impedances like this. There is a source, let's say from here to here, there is a source, and there is a detector between the other two ends. Now you see the source is usually grounded. So the detector that you use, you cannot use a CRO for example, because CRO one terminal is grounded. Okay, you can use a meter, an emitter or voltmeter, but emitters and voltmeters are not as sensitive as we want them to be in modern instrumentation situations. Since you are testing for null, you are trying to find out, you see two of them will be standard resistors, standard impedances, the third will also be a standard, the third will be a variable, the fourth is unknown, and you want to measure, you want to check the null, that is under which condition the voltage between these 2 points becomes equal to 0. So you should, for sensitive measurement, you should be able to measure very small signals of the order of microvolt, and that can be done only when this signal is amplified and then put to a meter. So what we do is we apply this to a differential amplifier, and the output then we can measure by means of a meter. Output can be connected, output detector can be connected to ground, one terminal can be connected to ground now, because this has caused a transformation from a balanced voltage is one neither of whose terminals are grounded, to an unbalanced voltage in which one of the terminals is grounded. So what we have done is balanced to unbalanced transformation by means of a differential amplifier, and this helps us in checking the null condition of the bridge. This is one of the very prominent uses of a differential amplifier, and any such transformation, just a side comment, any such transformation which transforms a balanced voltage to an unbalanced voltage is called a balloon, B-A-L-U-N, balanced to unbalanced. Can you give me another example of a balloon, very common example? Can we?
Something connected in TV areas.
TV areas, yes, there is a balloon there, but more common. You must have seen it in the laboratory many times. A transformer, an ordinary transformer, this voltage can be balanced, the output can be unbalanced. Okay? You can apply a balanced voltage here and an unbalanced, because there is electrical isolation, there is only magnetic coupling. A transformer is a balloon, balanced to unbalanced, or vice versa. You can also transform, there is no reason why this cannot be primary and this cannot be secondary. So unbalanced, balanced to unbalanced, or unbalanced to balanced.
Both are called balloon?
Both are called, okay. One is called balloon, the other is called unbalanced. Okay, that is not a very common term. But our interest is not simply in measurements. Our interest is in electronic circuits of all kinds, and the differential amplifier forms the input stage of most of analog integrated circuits. most analog integrated circuit chips, whether it is a phase detector or an amplifier or whatever it is, the input stage is a differential amplifier. Differential amplifier forms the heart of the operational amplifier, which you have known so far as a block. Inside the op-amp, the first stage and a few subsequent stages, they are all differential amplifiers. Differential amplifiers forms the input end of almost all analog integrated circuits, and of course you cannot do without it in an op-amp. The gain is basically obtained from differential amplifiers. The gain of an op-amp, this high gain 10 to the 6 of the order of 10 to the 6 is obtained from differential amplifiers. Now the desirability is, I have told you that the output is A sub D V sub D plus A sub C V sub C. Ideally we want A sub C to be equal to 0, ideally. So a measure of performance, a measure of goodness of a differential amplifier is obtained as the ratio AD by AC, and if it is ideal then this ratio should be infinity. So we want this ratio to be as large as possible, and to be able to ignore the phase inversion which may occur, we take the magnitude of this, and this ratio is called the CMRR, common mode rejection ratio, common mode rejection ratio. Okay, CMRR is defined as this ratio. Now this ratio can be very large, let's say 1000, a typical value. 1000 is a typical value. Instead of expressing this as a number, sometimes we express this in terms of decibels. So we multiply by 20, then take the log with respect to base 10 and express this in dB. A CMRR of 60 dB corresponds to a number of 1000. Alright, so CMRR is often expressed in decibels. Now what we want is therefore that A sub D must be much greater than A sub C. Okay, so if the signal to noise ratio at the output is denoted by S by N O, and the signal to noise ratio at the input is denoted by S by N I, then since AD is much greater than AC, the signal to noise ratio at the output would be much greater than the signal to noise ratio at the input. Why? Noise is the common mode. If you have two terminals here, the same amount of noise will be picked up by both. Alright? But the differential amplifier discriminates against common mode signals, and therefore the noise at the output, noise at the input will not be amplified, will be amplified only by AC, the common mode gain. The signal component will be amplified by AD, and if AD is much greater than AC, naturally this ratio at the output will be much greater than the ratio at the input. So signal to noise ratio is improved by differential amplifier. This is another bright feature of a differential amplifier.
Sir,
Yes.
so this sounds very good, but it's not understood. So how?
Okay. My signal is the differential signal, V1 minus V2. Alright. Whereas each terminal picks up some noise. This may be noise due to device, maybe noise due to extraneous circumstances and so on. So at the input you shall have signal and also noise. At the output also you shall have signal as well as noise. Signal will be amplified by a much larger quantity than the noise, and therefore signal to noise ratio at output shall be much larger than signal to noise ratio at input. Alright, because AD is much greater than AC. Noise is a common mode signal. Okay, that is the fundamental reason. I can write this relation in a slightly different form, AD VD plus AC VC. I can write this as AD VD, the ideal value, and the deviation I can put it in the form 1 plus VC by VD divided by CMRR, if it is a positive quantity. CMRR is taken as a magnitude, so we consider this as a positive quantity. And naturally, if V0 is to tend to AD VD, then CMRR must be much greater than the ratio of the common mode signal to the differential mode signal. This is another way of expressing the same relationship. Now, so far about the general terminology. Now let's look at a practical circuit. The circuit, try to draw with me, has two identical transistors, Q1 and Q2. Identical transistors, biased identically. That is, you have R sub C here and R sub C here. And these two are taken to a plus VCC. Alright. The emitters of the two transistors are coupled together. Coupled directly. They are connected together. So a differential amplifier is also sometimes known as an emitter coupled pair, ECP, emitter coupled pair. Two transistors whose emitters are tied together. Alright. In the current mirror, can you give another name to a current mirror?
Collector base.
No, base coupled. Two bases are tied together, so base coupled pair. This is an emitter coupled pair, and the one of the circuits uses a resistance here. We call this REE, a resistance from the common emitter terminal, and this goes to minus VEE, a negative supply. You will see that in integrated circuits, one always uses a positive as well as a negative supply. Usually this is same value, plus 12, 0, minus 12. Okay, this is the usual thing, but there is nothing sacred about them being equal. You can have a different story, but it is usually plus VCC, 0, minus VCC, so that the common point can act as a what? Ground, the zero potential. That sets the reference. Otherwise, integrated circuits are available as a package. You can connect any terminal to ground, your choice. But this reference of zero potential is set by the common point of the power supply. Okay? Then you have to the input, to the base, you have an RS, let's say 2, second transistor, a voltage source VS2. This is the signal, this is the RMS value VS2, and similarly you have an RS1. These are the two inputs, inverting and non-inverting. We will see which one is inverting, which one is non-inverting later. They can be interchanged, in fact, depending on where you take the output. The output voltages, now we shall first make a DC analysis of this. This is the circuit. This is the total circuit. We shall first make a DC analysis of this circuit. We will call this current as I sub EE, the DC current. We will call this voltage as capital V B1 between this point and ground. This voltage we will call capital V B2, this point and ground. This voltage we will call VC1 between this point and ground. The collector 2 voltage we will call VC2 plus minus, again between ground. And in addition and in addition I'll take another color. In addition, this voltage between these two we shall call as capital V, capital O, D with this polarity, VOD. All right. You notice a very interesting thing, that we have not used any capacitor in this circuit. We have not used any coupling or bypass capacitor, and therefore what would be its low frequency cutoff? DC. So this amplifier will be able to amplify right from DC up to some high frequency determined by the capacitors inherent to Q1 and Q2. So no low frequency cutoff. That's a very important characteristic of this amplifier. No LF cutoff. And I've already said Q1 and Q2 are identical. In the analysis, we assume that beta 1, 2 are much greater than 1 for both the transistors. In an integrated circuit, making two identical transistors is absolutely no problem. In fact, you make thousands in the same chip, identical transistors. Identical does not mean that betas shall be equal. Beta can have a spread, but nevertheless, if one of them has a beta of 150, the other cannot have a beta of 10. It will be 149, or at the most, let's say 151. It would have a spread, small spread. But nevertheless, we assume that beta 1, 2 are much larger than 1, which means that I sub C for both the transistors 1, 2 would be approximately equal to I sub E 1, 2. That is, the base current can be ignored. Alright? Base current can be ignored. Now, if I look at, let me draw it again. If I look at this part of the circuit, forget about what we connected there. This is VB1 plus minus. This is VB2 plus minus. I want to look at this part of the circuit from here to here. I want to come from ground and go like this, ground to ground. So I made a complete loop. In other words, I can write a KVL. And you notice that VB1 would be equal to VBE1 minus VBE2 then plus VB2. Agreed? Is that clear?
Yes.
Okay. So I can write VB1, the base voltage of transistor 1, minus the base voltage of transistor 2, which obviously is the input differential voltage. Input differential voltage. So I will call this, instead of writing VID, I shall simply write it as VD. I will not use I.
So the last analysis we did was totally for AC.
No, this is totally for DC. We are
So
saying
so the V0 is equal to AC PC plus AD.
that's right. We'll come back to that. We'll come back to that. From DC we shall go to AC. Okay? From DC we shall go to AC. These are all DC quantities now. VB1 minus VB2 equal to VD. I define this as VD. Therefore, this is equal to VBE1 minus VBE2. Okay? The differential voltage is simply equal to VBE1 minus VBE2. We also know that the collector current I sub C is equal to the reverse saturation current IS multiplied by e to the power base to emitter voltage divided by VT. This T is not threshold. Threshold for FET, it is thermal voltage. that is kT by Q, approximately 25 or 26 millivolt at room temperature, minus 1. And when the transistor is in the active region, VBE is a positive quantity, and this becomes approximately IS. The exponential term dominates, so I get VBE divided by VT, which means that VBE is equal to Vt multiplied by log of I sub C divided by I sub S. Alright? I can now introduce the subscripts. VBE 1, 2 shall be Vt. The two transistors are identical, so Vt shall be identical, and this will be IC 1, 2. Alright? And therefore VB, which was equal to VBE 1 minus VBE 2 shall be equal to Vt, yes, log of IC1 divided by IC2. Now we take the exponential of both sides. That is, IC1 divided by IC2 would be equal to e to the power Vd by Vt. Alright, we go back to the same circuit. We go back to the last but one slide, and you notice, now I'll use a different color. You notice that if this current is I sub C1 and this current is I sub C2, since we have ignored the base currents, the same current must flow here and here, IC2. So the emitter current, the current through REE is IEE is equal to IC1 plus IC2. Therefore, this gives us the second relation, that is I sub C1 plus I sub C2 is equal to IEE. You shall see later that we will try to maintain IEE as a constant, the total current. There can be a sharing between the two transistors. IC1 and IC2 may be different because of different voltages applied to their bases, but the total current we shall try to keep a constant. So these are two equations from which you can solve for IC1 and IC2. A little bit of algebra will show that IC1 is equal to I sub EE divided by 1 plus e to the power minus Vd by Vt, and IC2 shall be equal to I sub EE divided by 1 plus e to the power plus Vd by Vt. Alright, let us try to draw these expressions. Yes.
So if we apply the same signal here,
Same signal, I am not talking of signal at all. I am talking of the DC quantities. Signal will come a little later.
So
Yeah.
why will VB1 and VB2 be different?
Why do VBE1 and VBE2 be different?
Yes, sir. VB1, VB2.
Suppose they are different. Because the reason is clear. RS1 and RS2, we didn't make them equal. We didn't make VS1 and VS2 equal. So there can be a difference voltage between the two bases. Alright? Okay. If they are absolutely identical, then of course our purpose is served. We have an ideal differential amplifier. It is to take care of the non-ideality that we are going into this analysis. Now suppose we plot IC1 and IC2 versus Vd by Vt. Suppose we plot IC1 and IC2 versus Vd by Vt, and let's say minus 4, minus 2, minus 1, minus 3. Vd, as you can see, is the difference between VBE1 and VBE2. It can be positive as well as negative, depending on which one is higher. So we go up to 4, 2, 1, 3. Okay, and let's say, what is the maximum value that IC1 or IC2 can have? IEE, isn't it right? Both of them. When Vd is not 0, when Vd is infinity, very large, then this term drops out and we get IE. Similarly, when Vd is negative infinity, I get IC2 maximum as IEE. So the maximum value is IEE. You also notice that when the differential voltage is 0, Vd is 0, then both the currents are equal, IEE by 2. So both the curves must pass through this point, IEE by 2. And it's very easy to see, because of the exponential nature, that one of them will rise like this. Which one is this?
IC1.
IC1 or IC2?
IC1.
This is IC1. And IC2 naturally shall be like this. And they will be perfectly symmetrical, because the factors are the same, e to the Vd by Vt. You notice that if Vd by Vt exceeds 4, if Vd by Vt exceeds 4, IC1 is approximately equal to IEE, and IC2, I must label this is IC2. IC2 is approximately 0. What does this mean? It means that when VBE1 is greater than VBE2 by 4 times the thermal voltage, that is approximately 25 millivolts, so 100 millivolt is 0.1 volt, then which one? Q2 is cut. And what is the condition of Q1 then? It will be in saturation, because it passes the maximum available current. Okay, and therefore Q1 will be in saturation and Q2 will be cut off. On the other hand, when Vd by Vt is less than minus 4, that is when Vd is less than minus 0.1 volt, okay, approximately, Q2 becomes on and saturated and Q1 becomes off. And you can see the root of the reason why a differential amplifier can also work as a digital circuit. There is switching. If this differential voltage swings between minus 0.1 and plus 0.1, there is switching of the state of the circuit. One transistor on, the other off, now becomes the former one off, the latter one on. And therefore, this circuit, differential amplifier arrangement, is also used in a digital circuit, and this is what is known as the emitter coupled logic, ECL, emitter coupled logic. Our purpose is, however, analog, and therefore we want to see if we can get a linear relationship between the output voltage and the input voltage. Okay, this is obviously a nonlinear relationship. We don't want any transistor to be cut off. We don't want any transistor to be in saturation. So we must avoid them. Let us see how to avoid them. Now, if you go back to the circuit once more, let me draw this. This is C. There is an R sub C. R sub C, they are identical. This was equal to Vc1 plus minus between this point and ground, and this voltage was VC2 plus and minus, and this voltage was VOD plus and minus. You can very easily see, I am not drawing the rest of the circuit because that is not of concern. You can easily see that VC1 is equal to VCC minus IC1 times R sub C. Alright. Similarly, VC2 is VCC minus IC2 multiplied by RC. We know the plots of IC1 and IC2, therefore we can plot VC1 and VC2. Tell me, what will be the maximum value of VC1? VCC. And the minimum value?
VCC minus IE.
That's right. Not 0. VCC minus IEE RC. So that would be the variation. When the current is a maximum.
So what about VE?
What about?
VEE.
There is not a concern, because the output is taken from this point to ground. VE does not come into the picture. Alright? VE will come into the picture later. We will see this. But you notice that when the collector current is a maximum, this voltage is a minimum. When the collector current is a minimum, this voltage is a maximum. Now let us see what these plots are like. We are plotting VC1 and VC2. The maximum value is VCC and the minimum value somewhere here is VCC minus IEE R sub C. This is the minimum value, okay? And the voltages shall vary like this. Which voltage is this? VC2. And the other one would be like this. This is VC1. Now versus VD by VT. Okay? These are the two voltages. If I take the output voltage VOD, this is equal to VC1 minus VC2. Okay? Now, what is the maximum value of this? Maximum value is the IEE times RC. And what is the minimum value? Minus IEE RC. So the output voltage shall swing between plus IEE RC and minus IEE RC. And therefore, let's find out, let's draw a line of IEE RC here. Then I must go to minus IEE RC also. Okay? And the plot shall look like this. It shall look like this. It will swing between plus IERC to minus IERC, and this range very approximate. I should have drawn like this. This range is 2 and minus 2 approximately. The range in which the curve of VOD versus VD by VT is approximately linear. That is, if the VBE1 and VBE2 are such that the differential voltage lies between minus 2 VT, approximately minus 50 millivolt, to plus 2 VT, approximately plus 50 millivolt, then the variation of VOD versus VD is approximately linear. what I have shown here is a degraded picture. Actually it's highly linear between these 2 points, okay, and that can be obtained, that it is highly linear can be obtained by an exact analysis for VOD, okay, and the salient points are that VOD is equal to VC1 minus VC2, which is equal to can you tell me in terms of VC1 is VCC minus IC1 times RC, VC2 is VCC minus IC2 times RC, so it will be IC2 minus IC1 times RC, and you substitute the values of IC2 and IC1 in this expression, then you get IEE 1 by 1 plus e to the power plus or minus plus Vd by Vt minus 1 over 1 plus e to the power minus Vd by Vt. Which one will be larger if Vd is positive? Second term. Therefore I write this as minus IE second term minus the first term, and a bit of trigonometry, not trigonometry, hyperbolic trigonometry will show you that this is given by IEE. I made a mistake. RC. IEE RC, you can show that this is tangent hyperbolic Vd by 2 Vt. This simplification I leave it to you. The definition of tangent hyperbolic is sine hyperbolic divided by cosine hyperbolic, and sine is e to the x plus e to the minus x, no, e to the x minus e to the minus x divided by 2, no j, shin, and cos is e to the x plus e to the minus x by 2. So this is the expression VOD, and the plot of tan hyperbolic in the range, you see that 2 Vt occurs here, in the range Vd minus 2 Vt to plus 2 Vt is approximately linear. It's highly linear in fact, and that is how the differential amplifier can be used as an analog amplifier for linear amplification. And this is the point where we will start from next time.